Welcome to the Crystal Clear Electronics Studio. Here is the second video of chapter 22. In this episode, we will try out the AD converter of the Atmega microcontroller.
Of course, but first let's see the main features of the ADC built into the microcontroller that are relevant to us. It has 8 channels in asymmetric mode, and 7 differential input channels can be used in symmetrical mode. It works in a successive approximation mode. See the Outlook section of the written material for an explanation of this. It has a 10-bit resolution, a measurement range from 0 to reference voltage, an interrupt call when the conversion is complete, and a maximum of 15 kilosample per second at maximum resolution. In this microcontroller, the differential mode can be used by placing the negative signal on the ADC 1 pin and the other signal on one of the other 7 channels. However, this mode is only available with the TQFP packaged microcontroller and not with the DIP package. Nevertheless, in our example measurement, high noise immunity is not required. The asymmetric mode can be used as it is common in low-frequency measurements. The ADC requires 50 to 200 kHz clock for an accurate operation. If the 10-bit resolution is not required, the ADC clock can be over 200 kHz. We are satisfied with only an 8-bit resolution. The conversion takes 13 ADC clock cycles, except for the first conversion, because it takes 25. In our examples, the built-in RC oscillator is used to generate the microcontroller clock. The operating frequency in this mode can be set with bits 3 to 0 of the clock select register according to table 8.8 of the datasheet. These are the least significant bits of the clock select register. We want to set 8 MHz clock, which is achieved by setting the clock select bits to 0, 100. To produce a 50 to 200 kHz clock, which is suitable for the ADC, the microcontroller's 8 MHz clock is divided by 128 with the prescaler, which means a 62.5 kHz clock. From this, the sampling rate is approximately 4.8 kilosample per second.
Now let's get down to the practical part.
For the first measurement, assemble the following circuit. The task is a voltage comparator application. Compare the voltage of the potentiometer on PA1, this will be the ADC1 channel, with the voltage created by the voltage divider with the NTC, this will be the ADC2 channel. Use AD conversion for the measurement. If the NTC voltage is greater than that measured voltage on the potentiometer, the LED on the PA0 pin should light up, otherwise it should not light up. The figure shows the measurement layout. And here, I would like to note that for a better understanding, we recommend reading the datasheet simultaneously to the solution. When the circuit is ready, we can move on to the development of the software application. As a first step, we define the operating modes of I/O ports, whether they are configured as inputs or outputs, and we give them an initial value. Using a technical term, we initialize them. See function IOInit in the io.c file. In the port A, port B, port C, port D data registers, we turn off the pull-up resistors and define the pins as inputs, except for PA0 pin on port A, as this is an output because it controls the status LED. The clock is initialized in timer.c using the timer init function. The TCC-R1B timer counter control register contains the clock controller settings. The register bits are described in chapter 16.11.2 of the datasheet. Table 16.6 shows that if no prescaler is needed, then CS12 equals 0, CS11 equals 0, CS10 equals 1 must be set in this order. The other bits in the register are not set, they're not needed, so they remain at the default value of 0. As described in chapter 16.11.7, the interrupt of timer 1 is enabled by setting the TOIE1 bit of the TIMSK timer counter interrupt mask register, which is responsible for setting the clock interrupt. Finally, we enable interrupts globally. To initialize the ADC, you must first set the ADC reference voltage in the ADC init function using the ADMUX, that is, ADC selection multiplexer register, according to chapter 22.9.1, which in our case equals the external AVCC voltage. It means that we set REFS1 bit to 0 and REFS0 bit to 1. Using table 22.4, we select the register bits to set so that the first channel, the ADC1, is the input. For this, MUX0 must be set to 1. The remaining MUX bits can remain at the default value of 0, they do not need to be set. We set the ADC state flag to pot meter. It's important this variable is volatile because it is modified only in the interrupt handler function, and since that only accesses after an interrupt, the compiler will otherwise optimize the variable. The result of the ADC conversion is put into the ADCH and ADCL, that is, the high and low parts of the ADC data register. The figure shows how the format of the conversion result is modified by the ADLAR bit of the ADMUX register. For the sake of simplicity, we are now satisfied with the only upper 8 bits. The two smallest positional value bits are ignored. For this reason, it is more practical to use ADLAR equals 1 mode so that the result is left aligned in the ADCH register. ADC is enabled by the ADC enable function. In this function, we set the ADC control and status bits according to chapter 22.9.2 of the datasheet. The prescaler is set to 128 according to table 22.5 by setting the ADPS0, ADPS1, ADPS2 bits to 1. Furthermore, we enable interrupt and ADC as well. In the main program, we start an infinite while loop which controls the LED. If the voltage of the potentiometer is lower than the voltage of the NTC divider, then the LED should light up, otherwise not. The interrupt is implemented in the ISR function. The value of the CNTR counter is incremented until it reaches the maximum value, the CNTR max, which is defined as a constant value of 10. When the counter has reached this value, we set it to 0 and call the ADC start function, which does nothing else than set the ADSC bit of the ADCSRA register, that is, the ADC conversion is started. The timer settings and the CNTR max value could be different values as well, but then we would start the conversion less or more often. When the conversion is completed, another interrupt function is called, namely the ISR function. In this function, depending on the value of the flag ADC state, the voltage of either the potentiometer or the NTC is saved in the appropriate variable. The voltage is obtained by multiplying the result of the ADC conversion by the resolution, which in our case is dividing the 5-volt range into 256 parts, as we only use the top 8 bits of the ADC. This corresponds to a resolution of 20 millivolts. After that, we switch to the next channel using the next channel function. In this case, the input channel and the value of the status flag must be changed. If the value of the flag ADC state is pot meter, so the voltage of the potentiometer has been measured, then it must be switched to the NTC, which means that according to table 22.4 of the datasheet, the ADC2 channel, which has the NTC divider, must be chosen as input and the state flag must be set to NTC. In case of ADC state equals NTC, the reverse should be done. The input channel will be ADC1, which has the potentiometer, and the state flag will be a pot meter. After getting through the technical details, let's enjoy the results of our work a bit. Put breakpoints to lines, which control the LED in the main function, and add the counter, potentiometer voltage, the NTC voltage, that is the UPOT and UNTC variables, to the variables to be monitored. It can be done by right-clicking on the variable name in code and selecting Add Watch. Then, our variables will be displayed in the watch window. When running our program in debug mode, we can see the voltage measured on the potentiometer and the NTC divider in the watch window. When the counter has reached 10, one of the measured voltages is updated. Check the last bit of the port A register, the PA0, in the IO view window based on the value of U potmeter and U NTC. We can see if everything has been done well, if the voltage of the potentiometer, the U potmeter, is lower than the voltage measured on the NTC divider, the U NTC. Then PA0 is 1, so the LED is on, otherwise PA0 is 0 and the LED is off. As a practice, let's try setting the voltage on the potentiometer to 2 volts.
That brings us to the end of the first application of chapter 22, but before we say goodbye, I would like to show you the device I have in front of me. You may have seen something like this before. It's a VFD clock. Nixie tube clocks are very similar, but this one is a VFD. A VDF clock shows the time as default, but also has a temperature measuring function, which you can see here. This device is not much more complicated than the one shown in the previous example. On the circuit board, there is an analog temperature sensor. Here, it is on the very edge, which provides a continuous analog signal, a voltage value as a function of temperature at its output. This voltage value is measured by the PIC microcontroller inside the device using an AD converter. Then, from the measured voltage, the PIC calculates the temperature voltage characteristics in the datasheet of the thermal sensor, and it displays it on these VFD tubes. Currently, we are sampling very slowly, every 2 seconds. The AD converter in the PIC is 10-bit, which means that at a supply voltage of 3.3 volts, the LSB is about 3.2 millivolts. Based on the IC characteristics of the thermometer, this would give a resolution of about 0.16 degrees Celsius. But of course, our application will be far from accurate due to measurement inaccuracies. However, for average household use, this configuration is more than adequate. By the way, another interesting thing about the device is that, as you can see here, it also has a few more exciting and interesting solutions. Here, you can see, for example, a resistor ladder soldered in this sideways position. This was simply because I happened to order a different kind of step register, an open drain one, which can only output the low logic level, not the high. I just didn't think it was that important, so I didn't wait for the normal one, the open drain IC, to arrive, but solve the problem this way. That's why you can see this little yellow wire here. If you follow the crystal clear electronics videos, you can also make similar devices. But now we are saying goodbye. Stay tuned for the upcoming video where we'll show you another exciting application. Bye!
Bye!